All right, let's talk about an incredible story. It's one that connects ancient shipwrecks, secret wartime projects, and, believe it or not, the very architecture of the device you're watching this on right now. I mean, just let that sink in for a second. This single sentence from researchers hints at a massive technological mystery. It's basically saying there was this piece of super advanced ancient tech that just, poof, vanished from the world for over 1,000 years. It sounds like something straight out of science fiction, right? But this story starts with a real-life discovery that had scientists scratching their heads for decades. And it's a discovery that really forces us to rethink the entire timeline of technology. So let's go back in time. The year is 1901. A team of Greek sponge divers are exploring a Roman-era shipwreck off the coast of a little island called Antikythera. They're expecting to find the usual stuff, statues, pottery, that kind of thing. Amidst all the priceless artifacts they bring up, there's this one thing, this lump. It's just a corroded chunk of bronze and wood, and for 2 whole years, it just sat in a museum in Athens, completely unnoticed. Everyone just figured it was another piece of junk from the wreck. But then, an archaeologist spots something. A tiny, precision-engineered gear wheel stuck right inside it. And that one little detail? Well, it changed everything. This was no ordinary lump of metal. This thing was the Antikythera mechanism. Using modern scanning, we figured out it's this incredibly intricate, hand-powered machine. We're talking dozens of bronze gears all meshing together perfectly, designed to model the entire cosmos. Now, unlike your phone or laptop, which uses ones and zeros, that's digital, this was an analog computer. It used the physical rotation of its gears to track the sun and the moon, predict eclipses with frankly shocking accuracy, and even time the 4-year cycle of the ancient Olympic Games. How wild is that? So the very existence of this machine creates this massive historical puzzle. I mean, if the ancient Greeks could build this, what happened to that knowledge? Why didn't it kick off some kind of industrial revolution in the Roman Empire? 1,500 years. That is roughly how long it took for humanity to create another machine that was anywhere near this complex. For 15 centuries, it's like the instruction manual for this kind of technology was just lost. And this timeline just shows you how huge that gap was. It's not just that progress kind of stalled out. Nope. This was knowledge that was profoundly and completely lost. The entire art of complex mechanical computation had to be reinvented from the ground up. Okay, let's jump way, way forward to 1946 to a thing called the Moore School Lectures. World War II is over, and this is a massive moment where all the top experts in the world got together to share the blueprint for modern electronic computing. It was basically the starting gun for a whole new technological race. Now, the Americans had just built this behemoth called ENIAC, so you'd think they were miles ahead. But here's the twist. A group of British engineers, fresh out of top-secret wartime projects, were about to completely surpass them. So what was their secret weapon? Well, it was experience. They'd spent the entire war building ridiculously complex electronics, like code-breaking machines at an unbelievable speed. They were masters of building things fast, trying them out, and improving them on the fly, and that gave them a critical edge. And so you get to the beginning of 1950, and here's a remarkable fact. Every single working, stored program computer on the planet had been built by engineers with that British wartime experience. They had simply figured out the key technical problems, like computer memory, faster than anybody else. But look, building the hardware is only half the battle. Once you've got a working computer, how do you teach it to understand numbers? Especially tricky things like negative numbers. This is where the story shifts from engineering to pure logic. See, at its most basic level, a computer has to turn everything, and I mean everything, into the language of numbers. But there's more than one way to write that language. And the system you decide to use has massive, massive consequences down the line. So one of the first ideas, called signed magnitude, seems pretty intuitive. You use one bit, one little switch for the sign, plus or minus, and the rest for the number. But here's the problem. You end up with 2 ways to write 0, a +0 and a -0, which just complicates the circuitry. The solution, the one that is used in virtually every computer today, is called 2's complement. It is a super clever way to represent negative numbers that gets rid of the 2-0 problem and makes doing math way, way simpler. The genius of this whole system is in what you could call the negabit. Instead of treating that first bit as a sign, the computer treats it as a large negative value. This is a simple but powerful idea because it means the computer can do subtraction by just doing addition. So, to calculate 7 minus 3, it just calculates 7 plus -3. That little trick makes the hardware for arithmetic incredibly simple and fast. But here's the catch. When the very strict rules of this machine language aren't handled properly, the results can be absolutely catastrophic. A tiny error deep down in the binary code can snowball into a real-world disaster. And in 1991, this is exactly what happened. The clock in the Patriot missile defense system measured time in tenths of a second. Well, the number 1/10 in binary is an infinitely repeating fraction, kind of like 1/3 is in our decimal system. The computer had to cut it off somewhere. And that tiny, tiny rounding error, accumulating over 100 hours, meant the system miscalculated a target's position by over half a kilometer. Tragically, that failure led to the loss of 28 lives. Then, in 1996, it happened again with the Ariane 5 rocket. This time, it was an overflow error. The best way to picture it is trying to pour a gallon of water into a shot glass. A huge 64-bit number representing the rocket's velocity was being copied into a much smaller 16 variable. It just didn't fit. That was the value of the rocket that veered off course and exploded just 30 seconds after it launched. The entire guidance system just shut down, all because one number was too big for the box it was supposed to go in. You know, when you take a step back, it's pretty amazing. From the bronze gears of the Antikythera mechanism to the silicon logic gates inside your phone, our quest has always been the same: to create machines that can model our world. There's this unbroken thread that connects that ancient astronomer carefully crafting his gears to the modern programmer carefully choosing their data types. They're all trying to perfect the language between us and our machines. It's a pretty humbling thought, isn't it? The story of the Antikythera mechanism is this powerful reminder that truly groundbreaking knowledge can just get lost. And it really leaves you wondering, what revolutionary ideas might we be overlooking right now? What's just out of sight, waiting to be rediscovered?